All right, let's get started. Welcome everybody to the special year seminar on theoretical machine learning at the Institute for Advanced Study. Today we are delighted to have a scientist as distinguished as Professor Avrim Blum as our speaker. Avrim is a professor and the chief academic officer of the Toyota Technological Institute at Chicago, and previously spent 25 years as a professor at Carnegie Mellon University. He's known for his broad array of contributions to semi-supervised learning, clustering, planning, differential privacy, computational social choice, and graph algorithms. He has served as the program chair for Fox, ITCS, and CODE, and also as the chair of the ACM SIGAC Committee for the Advancement of Theoretical Computer Science. He's a fellow of the ACM and is the recipient of the AI Journal Classic Paper Award, the ACML Code's 10-year Best Paper Award, and the Sloan Fellowship. Please welcome Avrim Blum.
Thank you. It's great to be speaking in the series. Thank you very much. Good afternoon, everyone. Okay, so I'm going to talk about a couple pieces of work in the area of sort of fairness and strategic classification. So we're looking at learning in the presence of biased data and strategic behavior. And various parts of this talk are joint with Saba Ahmadi, a student at University of Maryland who's visiting Northwestern, Hedya Bayagi, a postdoc at Northwestern and TTI Chicago, Kazia Najita, a student at TTI Chicago, and Kevin Stengel, a student at TTI Chicago. Okay. Let me just get my things set. There we go. Okay, so the first topic is about fairness and bias, and this part is joint work with Kevin Stengel from a paper, Recovering from Biased Data, Can Fairness Constraints Improve Accuracy, that just appeared in the recent fork Foundations of Responsible Computing symposium. Okay, so here's kind of the one slide version of this part. So usually in machine learning, we think of a trade-off between fairness and accuracy, or between different fairness constraints themselves. But what if the training data that we're optimizing over is biased? Could the fairness constraints actually lead to improved performance, even if all we care about is accuracy? So, I mean, normally if you're doing some optimization and you add a constraint on it, it's only going to make your optimum solution worse. But if you're optimizing the wrong thing, well, then maybe these constraints could actually make your solution better. And this is motivated by work of Kleinberg and Raghavan on a similar question in a ranking context, and also by the Hart-Price-Rebro fairness notions. And so what we'll do is we'll posit some simple ways data could be biased and examine whether existing fairness notions might help out or hurt. Okay, that's kind of the one slide version of this part. Okay, so just to kind of set the background. So, why fairness? So, algorithms are increasingly being used to automate or advise decisions that impact people. Topics like whether to be approved for a loan, whether to be admitted to a college, whether to be hired for a job, bail and parole decisions. And it would be a big problem if these algorithms were systematically biased against some racial or ethnic or gender group. And this question really kind of really hit consciousness in the study that was done by a group at ProPublica of the COMPAS software for aiding parole decisions. So this is a software for predicting recidivism, meaning going back to a life of crime, used as an aid in bail and parole decisions. And what it does is it classifies candidates as either low risk or high risk. And this study by Larson et al. And ProPublica looked at data and found that Black defendants who did not recidivate, did not reoffend over a 2-year period, were nearly twice as likely to have been classified as high risk compared to white defendants. And in the other direction, the white defendants who did reoffend within the next 2 years had been labeled low risk almost twice as often as the black reoffenders. So if you want to think about this as a binary prediction problem, so let's see. Let's say that positive is a good thing. So not reoffending over the next 2-year period is a positive example. And let's say that the classification, so classifying someone as low risk is predicting positive and high risk is predicting negative. What this is saying is that the false negative rate, so the fraction of true positives that were predicted negative was much higher for black defendants than for white defendants. And in contrast, the false positive rate, the fraction of negatives that were predicted positive was much higher for the white defendants compared to the black defendants. Okay, so that's troubling. Shortly after, there was a paper by Flores et al. In the Federal Probation Journal that said, well, on the other hand, the COMPAS system is calibrated. So if you look at the people who it calls high risk, there's about a 75% rearrest rate across both groups. And of those it calls low risk is also about a 30% rearrest rate across both groups. So the meaning in some sense of high risk and low risk is kind of the same across the two groups. Okay, or to put it another way, the probability of the truth given the prediction are similar for the two groups, but the probability of the prediction given the true value are not the same. And since these two quantities are connected via Bayes rule, and the two groups, which has a denominator in it, and that denominator is called the base rate, and those base rates are different for the two groups, it's not surprising. It's not possible to make, both probability of true given prediction be similar and probability of prediction being true given true being to be similar. Okay, so so these sort of studies motivated kind of looking at fairness and trying to come up with mathematical definitions that could be analyzed. And I want to just list a few different definitions of fairness notions that we might want. And just to kind of maybe make things, let's not talk about parole. Let's talk about things like getting into a college, getting a loan, getting a job. Okay. So one notion by Hart, Price, and Cerebro is called equality of opportunity. And the definition is as follows. We'll say that a predictor, so we're talking binary prediction, satisfies equality of opportunity with respect to a set of groups, G, so G is a collection of groups, if the probability of predicting positive, given that you're a true positive, is approximately the same across the different groups. Okay, so what this notion is saying is that one way to think of it is that if you know that you would be a good student, that you would be a good employee, a good borrower, you should have roughly the same chance of being admitted to the college, hired by the company, or approved for a loan, regardless of which group you belong to. Okay, so that's called equality of opportunity. A stronger notion called equalized odds says, oh, in addition, we would like this to be true also on the negative side. So we want equality of opportunity only requires this to be true on the positive side. Equalized odds also requires this to be true on the negative side. The probability of predicting negative, given that you're a true negative, should also be approximately the same across the groups. And one thing you might wonder is it possible to achieve this? And well, sure it is. For example, if you give everybody a loan, label everybody positive, then the probability of, you predict positive on everybody, then the probability of predicting positive given you're a true positive that you really would have paid back that loan is 100%. The probability of predicting negative given your true negative is 0%, regardless of your group. And so is predicting negative on everyone. So is predicting randomly on everyone, but crucially also so is predicting correctly on everyone. So if you're able to correctly, the predictions you're able to be correct on everyone, that would satisfy equalized odds. Okay. So that's these two notions. Another one is calibration, which I talked about briefly. So we'll say a predictor is calibrated with respect to a set of groups if it's the flip side. The probability of that's a true positive given you predict positive and the probability of being a true negative given you predict negative, that those are approximately the same across the groups. So another way you can think of this as kind of the meaning of predicting positive or negative is the same. Predicting positive means, there's an 80% chance they're positive or whatever, is about the same regardless of the group. And then one additional notion I want to mention is what's called demographic parity. And so we say a predictor satisfies demographic parity with respect to a set of groups if the probability of predicting positive is about the same across the different groups. Okay, so for instance, for say admissions, this would be, you'd have demographic parity if you admit the same fraction of applicants across the different groups. Okay, so that's called demographic parity. And many of these can be in conflict with each other, as we saw, for instance, calibration and equalized odds. And there's been a lot of discussion, about which pros and cons of different ones. But kind of the angle I want to take here is to look at the ability of these to address bias training data. So one commonly cited reason why you might have bias in classifiers is that often training data can be biased, and this can be reflected and even amplified in the classifier that you learn. Okay, so the angle that I'd like to take is, instead of arguing about which fairness notion is the right one, let's just consider some natural ways that training data could be biased, and then see if these constraints could actually improve accuracy of the classifier produced. Okay. So that would give, if they did, then that would give additional motivation for that particular fairness notion. And just one caveat is, as with, much theory, we are going to be making various assumptions. We're making a number of assumptions, some realistic and some less so, on both the way data is biased and on the form of the ground truth target function being that we're learning. So this is kind of a first step, I would say, and I'm not claiming that we're solving the problem. I think there's a lot more to do here. But we'll be making, some clean assumptions that we can then analyze, and then we can argue about whether they're realistic or not. All right. So let me get to our setting. So the setting is, we'll be looking at the case of two groups, A and B. A will be the advantaged group, and B is the disadvantaged group. So here they are. The groups are disjoint. We'll assume that membership is observable, so you can tell whether someone belongs to group A or B. And we're interested in binary classification. So who gets approved for a loan or hired or admitted. Okay. So some sort of binary classification problem. In general, this will not, we will not be in a realizable setting. So say in all my pictures, the blue dots will be the positives and the green dots are the negatives. And here we have a linear classifier, and it's not perfect, but it does a pretty good job. Okay. There is be some true distribution on example label pairs for group A, and another distribution on example label pairs for group B. Okay, so there'll be one for A, another for B, and we'll be imagining classifiers that are allowed to do different things on the members of group A and group B. Okay, membership is observable, and so they could do one thing on people in group A and another thing on people in group B. If you don't like that, and then you could imagine, okay, membership is not observable, but there's lots of features, and this system is going to be able to sort of figure out what group you belong to from other features, and then be able, in its optimization, to do different things on the members of group A and group B. It is important for the question we're asking that these two distributions, DA and DB, look different, because we're going to be interested in cases where the training data is biased, in particular the folks in group B, that the training data is biased on them. And if really these were the same, then you could get around the problem by simply throwing out all the members of group B and only training on the group A folks where it's not biased in our models. In any case, it's going to be more interesting, the problem we're looking at, if we imagine that these distributions are different. The overall distribution is then a mixture of these two. So R is just the fraction of group B. So every point with probability R is drawn from group B, and probably 1 minus R is drawn from group A. So that's the overall mixture distribution. And the algorithm we're looking at is you simply take a lot of data and perform ERM. So take a lot of data and just find, say, the linear classifier of, smallest error on the training data. We're going to be interested in the large sample limit. So there's going to be lots of training data. So not really worrying about, the generalization error. So it doesn't have to be linear separators. Any family where we don't have to worry about generalization error, we have lots of data. We find the thing that on our training data, looks best. So really, if our training data was indeed drawn from D, we would be doing great. The problem is our training data is going to be biased and not actually look like it's coming from D. Okay, that's the setting. All right, so now what I want to do is say a little bit about the bias model. So what kind of bias, might there be? We're going to talk about a few different kinds of bias that I think are reasonably natural. So the first kind we call underrepresentation bias. So what is this? So in this form of bias, what's happening is that group B shows up less in the training data than it should, less than its, that the true proportion is R, but it's showing up less often. And moreover, that the rate of showing up might differ for the positive and negative examples. So how might this happen? Well, for instance, if, your company has not done a good job of hiring people from group B in the past, then folks in group B, might be less inclined to apply. And moreover, the positive examples, the ones who are more well qualified, they may have more outside options. They might be even less likely to apply compared to the negatives, the ones who are less well qualified, who might not have as many other options, so they'll apply anyway. Okay, so you might end up with this sort of, underrepresentation where the amount of underrepresentation is not the same for the positive and negative examples. Okay, so formally, this bias looks as follows. You draw an XY pair from the overall distribution D. If the X is coming from group A, you keep it. If it's coming from group B, you look at the label. If it's a positive label, you keep it with probability beta plus. If it's a negative example, you keep it with probability beta minus. And beta plus and beta minus might be different from each other. Okay, so that's underrepresentation bias. Okay, so we'll be looking at that as one of the models. All right. Another model is labeling bias. So here we imagine that people show up, but the labels are being done by maybe people who themselves are biased. So the positives of group B might be mislabeled as negative in your training data with some probability nu. So for instance, maybe where the labels came from was past hiring managers who were looking at resumes, and if they themselves were biased, they might have, mistakenly, or well, they labeled maybe some of the positives as negative. So each positive, say the positives are the blue points, each one with probability nu is mislabeled in the training data as negative. Okay, and that's only happening for the folks in group B. Okay, so maybe the ones I just circled in red got, they look negative in your training data. Okay, so formally the model is you draw an XY pair from distribution D, and if the example is coming from group B and the label is positive, then independently you flip it to negative with probability nu. So it's really a true positive, but the label you observe is negative. Okay, so that's the bias in the we call labeling bias. All right, and then we can also consider both of them happening. That there is kind of a combination. That there's folks in group B maybe not showing up at the the true rate, and maybe that being different for positives and negatives, and that when they're labeled in the training data, that because of bias in the labelers, that the folks in group B, some fraction of the positives got mislabeled as negative. Okay, so now let's take a look. So again, we'll be considering all the effects of all of these in the large sample limit. Okay. Good. All right, so now we're going to also make some assumptions about the ground truth. Okay, so I think those bias models are reasonable ones to study. The assumptions we're going to make about the ground truth, I think you could argue with, okay, maybe these are too simplistic. But let me just tell you what we're going to be able to analyze. So first of all, some guiding principles in the way we're going to set things up are one, we'll be interested in the case where there's no perfect classifier. And the reason for that is that the underrepresentation bias is not so interesting in the large sample limit if there's a perfect classifier. So if I tell you, the positives and negatives in group B aren't showing up at the correct rates and even they're different, if there's a perfect classifier, you just see enough data, you just take a separator, right? I mean, it's okay if you didn't get the right proportions in the large sample limit anyway. So it's more interesting what happens if there isn't a perfect classifier. On the other hand, what we do want is I would like a situation where the ground truth satisfies the fairness conditions over the true unbiased distribution. So if the ground truth doesn't satisfy the fairness conditions that we'll be looking at over the true unbiased distribution, then there's kind of an intrinsic conflict that you've already set up between fairness and accuracy. So I'd like to not do that. So I want to at least set things up so that things are okay before the bias happens. Okay, so with that as guiding principles, here is specifically what we'll assume. So two things. The first thing we'll assume is that there exist Bayes optimal classifiers, HA star and HB star, in some families, capital H, maybe linear separators, maybe something else. So for instance, these red lines here, so this could be HA star right there, and this might be HB star right here, okay? And such that for any example X independently, and for both groups, the label, the true label Y, is equal to H star with probability 1 minus eta, and is the opposite of H star with some probability eta, where eta is something less than a half. Okay, so eta is the intrinsic error rate of these Bayes optimal classifiers. So I think in these pictures, this was showing, I think it's basically a quarter. 1, 2, 3, 4. Yeah, it's roughly 25% error rate here. And the errors are uniformly spread. So think of it as, we have our data points, and now each one independently is labeled according to H star with probability, say, 3/4, and the opposite of H star with probability 1/4. So we're assuming that these Bayes optimal classifiers, they do make mistakes, but those mistakes are kind of evenly spread through the space. If you're familiar with classic computational learning theory, this is equivalent to what's called the random classification noise model, except Y here is the true label. So it's not like H star is a true label and then you observe a noisy version. Y is the true label, and H star is just kind of the best you can do given the features that you have. Okay. The second thing we'll assume is that for both groups, the fraction of examples on which H star predicts positive is P. It's the same. So we'll call that P. So it looks like this. A P fraction of points are above the line, and a 1 minus P fraction are below the line for both groups. So here we're saying that these Bayes optimal classifiers satisfy demographic parity, that they classify a P fraction of the folks of group A as positive and a P fraction of the folks of group B as positive. Okay? So just to notice, given our assumptions, okay, so these Bayes optimal classifiers satisfy demographic parity. They also are calibrated. Why are they calibrated? Because we said, given that you're above the line, the probability you're labeled positive is 1 minus eta, and that's true for both groups. And given that you're below the line, the probability you're classified negative, it's also 1 minus eta for both groups. So it agrees for both groups. So these Bayes optimal classifiers are calibrated. Okay, and because of these together, we also have that they satisfy equalized odds and equality of opportunity. Okay, so we'll just abbreviate both of them as EO. So they both satisfy EO. Why? Well, because that's basically there we're asking, given that you're positive, what's the probability that you're above the line? So so what fraction, instead of asking what fractions above the line are blue, we're saying, hey, what fraction of the blue points are above the line? And so we can just calculate that. Well, so we can just do, do Bayes rule, right? So it's just the probability that you're, above the line given that you're blue is the probability that you're blue given that you're above the line, which is 1 minus eta, times the probability you're above the line, which is p, divided by the overall base rate, the probability of being blue, which is p above the line times 1 minus eta, that's the blues above the line, plus 1 minus p times eta, which is the blues below the line. And that's the same for both groups, right? So for both groups on the unbiased data, yeah, these Bayes optimal classifiers satisfy demographic parity. They're calibrated. They satisfy equalized odds, equality of opportunity. Great. Okay. All right. So now what happens? All right, so let's think about underrepresentation bias. And let's think about the most interesting case here is beta minus is 1. So all the group B negatives show up, but let's start slowly tuning beta plus from 1 down to 0. So positives just start disappearing. So as we tune beta plus down, let's imagine, positives start disappearing. And so at some point, we've gotten rid of some positives. And ERM all by itself will actually be fine. It will do the right thing, producing the correct A star, HA star, HB star, until beta plus gets small enough that above the line, there's actually a higher fraction of negatives than positives. So in particular, once I keep crossing out blue points, and and I do it until beta plus gets below eta over 1 minus eta, at that point, above the line will be more negatives than positives, and all of a sudden ERM will say, okay, forget it, I'm going to classify all of B as negative, because that'll be the best, it's going to look, and that will be the optimal classifier. So it'll still do the correct thing on the A's, but all of B will be classified as negative. So basically ERM without any additional constraints will do the correct thing for a while, and then once beta plus gets small enough, we'll classify all of B as negative. All right, so that's what's going to happen. All right, well, what about if we add some of these fairness constraints? So what about calibration? So calibration is kind of interesting. So what is that going to do? So let's imagine that, some of the positives of group B don't show up. Okay, so, and even if it hasn't gotten to the point where ERM wants to, maybe there's still more positives and negatives above the line. Nonetheless, what does calibration do? So calibration is going to say, what it wants is the purity kind of above the lines for A and B to match. So if you notice, look that on the A side, the positive portion here, right, is a lot more blue than the positive portion on the green on the B side. So the A side, the positive side, is more pure than the B side. And so how do you fix that? Well, the only way to fix that, what calibration is going to do, is move the red line down to equalize the probability of, so here I'm talking about the probability of a true positive given you predict positive. So what fraction of points above the line are blue, are true positives? And the only way to equalize that will be to move the red line down to basically allow more unqualified A's in. And secondly, on the negative side, you'll notice that on the B side is more pure on the negative part, because there's more, the ratio of greens to blues is closer, is higher on the B side than the A side. And the only way to fix that is to raise this line on the B side. So to satisfy calibration, as you bring beta plus down, it's going to have to predict negative on qualified B's. It's going to have to lift the HB star and predict positive on some unqualified A's, reducing the HA star. So it's actually going to make things worse, right? It's going to be biased in just the wrong, the bad way. Even with, if for any value beta plus is less than 1. Okay, so that's problematic. What about demographic parity? Demographic parity, well, if these folks don't show up, then what's going to happen is a smaller fraction of the folks in group B are above the line. And so it will require class to equalize this. You'll end up having to classify some of the negative region of B as positive or some of the positive region of A as negative. So it's kind of, you know, if the first happens, that's kind of helpful for B, but it does reduce accuracy. Okay. On the other hand, equality of opportunity and equalized odds will actually do the right thing. They will allow HA star and HB star to go through because, you know, the probability of predicting positive given your true positive hasn't changed. So why is that? Well, the chance of somebody not showing up depends only on their label, not on whether they're above the line or below the line. So the blue points that show up still have the same ratio of above to below the line because you know, they showed up. So the ones who didn't show up, and the ones who did, they showed up. And you know, whether you showed up or not depended on your true label, not on where you are in this picture. And so the fraction of blue points that are above the line, it hasn't changed. And the same for the negatives. For the green points, they haven't changed at all. So equality of opportunity, equalized odds will allow the Bayes optimal classifiers to go through, but more than that, they will actually lock in the Bayes optimal classifiers. Because even if beta plus gets small enough where regular old ERM would want to just classify all of B as negative, it would just lift up that red line and just classify all of B as negative, it can't do that because you would no longer satisfy equality of opportunity. You would have to classify all of A as negative also. And so the A's will actually help ERM lock in the correct answer on the B's. And actually ERM will correctly produce HA star, HB star until, you know, finally you get to beta plus equals 0, and then these probabilities are undefined because you're conditioning on something of probability 0, right? But up until that point, they will do the right thing. Or if you set your parameters such that you get to a point where actually ERM will just say, you know what, I'm going to classify A and B. Everybody is classified as negative. But that would require actually very extreme parameters, especially if A is a majority. You might not even get that. So it's interesting. In this case, equality of opportunity and equalized odds will stop ERM from doing, you know, saying, hey, I want to classify B as negative, and sort of lock in the correct answers. Okay, so that's what happens with underrepresentation bias. Let's take a look at, I didn't want to do that. Okay, I clicked on the wrong thing. Okay, what about labeling bias? So labeling bias, so what if, you know, some fraction of positives are mislabeled as negatives? So now it's not they're not showing up, but they are mislabeled as negative. Well, ERM will do the right thing until the error rate is such that above the line you have more green points than blue points. So actually at this point, you know, right now we have 6 green points and 6 blue points. So it's just at the tipping stage, and one more and boom, it's going to label everybody in B as negative. So once the noise rate gets greater than this quantity here, ERM is just going to label everyone above the line as negative in group B, and so it's going to classify all of group B as negative. Okay. Equality of opportunity still works here. It will still continues to lock in the correct answers. And the reason is that the probability of predicting positive given your true positive hasn't changed. So HA star and HB star is still allowed. And it also, and they're also now HA star is protecting HB star here, because if you try moving your classifier up for B, it's going to force you to do the same thing for A, and that would increase your error rate. And the ERM is trying to minimize error subject to this constraint. And so the HA star being locked in position will help lock HB star in position too. Okay, so why is probability predict positive given true positive the same? Well, because if you look at the blue points that are left, they still are in the same ratio. So if you're a blue point that was not mislabeled as negative, you still have the same chance of being above versus below the line. So that stays the same. Actually, in this case, demographic parity does the right thing also. And unfortunately, equalized odds, which requires equalizing the negative side, that one, unfortunately, no longer does the right thing. The problem is that even though the blue points are correctly balanced on the B side, the green points aren't. The green points are now much, they used to be much more likely below than above, but now they seem to be kind of closer to 50-50 because you've got all these mislabeled positives, and more of them were on the positive side than the negative side. So if you look at the points that I circled here, right, a lot more of them were on the positive side than the negative side. So if you add them to the green set, all of a sudden the fraction of green points above the line has changed from B to A. And so equalized odds is going to force doing some funky things with the classifiers. And calibration continues to force the classifier to favor group A and hurt group B, because it's going to try to equalize these superiorities above and below the line. And the only way to do that is to allow unqualified A's onto the positive side, to basically move the A line down, and to reject qualified B's, to move the B line up. So it's going to do this the wrong thing. Okay. Both together. So both together, actually, equality of opportunity will continue to lock in the A star and HB star until the bias is so overwhelming that ERM would rather classify all of A and B together as negative. So basically, it's the optimal solutions, depending on the parameters, is either do the correct thing, classify all of A and all of B as negative, or if you set the parameters, you can set it so that you want to classify all of A and all of B as positive. But assuming that those aren't it's not so extreme as that, then they will actually lock them in, even when regular ERM would give up on the B's and classify them as negative. Okay, so so just kind of summarize this portion of the talk. So these are very stylized models, in particular of the correct labeling function, but also of how data is biased. But I think they give an interesting way to compare fairness notions. And what I think is interesting here is these specific results. They give another motivation for using equality of opportunity, which is namely that this particular fairness notion can actually improve accuracy if the training data is biased in these ways, and under this ground truth model. Whereas, in contrast, notions like calibration actually force your classifier to compensate in exactly the wrong direction, hurting the folks in Group B who are being biased against, even when regular ERM wouldn't do that. Now, these are highly stylized models. I think there's much more to be done, but I think it's a first step. Okay, so that's part one. And then I want to talk about something kind of completely different. Okay, good. And then we can discuss. We can have questions on both parts. Okay. So the second part I want to talk about is strategic online classification, and this is joint work with Saba Ahmadi, Hedia Behagi, and Kizia Najita. Okay. So here I want to talk about a different kind of bias. So here we're again thinking about classifying, people, but the issue is different. So here we're classifying entities that will aim to modify how they appear in order to be labeled positive. So again, let's think of cases like, deciding who gets a loan, admission to college. But now we're thinking these are features to these points in space. What is points in space? These are features. And these features can be changed by the data points. They can be the things you can observe. They can modify them to some degree. So we'll have a model where agents can modify their observable feature values at some linear cost in how far they move. Okay, so they're going to have a benefit they want to be classified positive, and if they can do some actions that make them look more loan worthy, or look like they should be admitted more by joining some club or whatever it is that they didn't really do much for, then they'll do it. And the challenge that we're going to be looking at in an online classification scenario is that as you learn and modify your decision rules, the agents will change how they manipulate, how they react to your decision rule. So you change how you classify, they're going to change how they respond to you. And this is particularly a challenge in the online learning setting. So we're not going to be making, in this case, any distributional assumptions. So in the first part of the talk, we were looking at probability distributions. Here, it's just an online arbitrary sequence scenario. So because of this, you can't have a training phase where, let's say, in the beginning part, you either give everybody a loan or give no one a loan, just to give nobody any reason to modify their features in order to collect sort of clean and manipulated data. And then if you did that and you knew kind of what their costs were, you could then maybe do some computation to figure out, what would be a good classification rule. Here, it's an informational problem that the only way you get data is by giving a classification rule, and then people manipulate based on the rule you give. So it'll be an informational problem in addition to a computational problem. All right, and kind of in some sense, this is, if this means something to you, this is a lot like online learning of what's called a Stackelberg leader strategy in a game. Okay. So this kind of topic comes up, in all sorts of places. So in business schools have come up is called measure management. So measure management is talking about where you're trying to measure performance of employees and using some quantitative measures, but maybe they were intended to measure certain things about them, but once you start measuring something in a quantitative way and people are aware of that, then they'll modify their behavior to optimize the measure rather than do what you intended. And so these notions of something called Campbell's law and Goodhart's law. And there's a really nice book that I like on this. It's called What Counts and What Gets Counted. So it kind of making the distinction between the thing you actually care about, what counts, and the thing that you're measuring, what gets counted. Okay. So here's the formal model that we'll be looking at. So first of all, we'll be looking at binary classification. So like before, and in this case, actually, I want to think of there being a perfect classifier. So for the kind of analysis we'll be doing here, we will assume that there's a perfect classifier. The agents, the data points, arrive one at a time. We have at any given time, we have a decision rule, a classifier that will make a decision of positive or negative. Then we'll be told the correct answer, and our goal is going to be to minimize the number of mistakes that we make. Okay, so a classic sort of mistake-bound model. The agents have the ability to manipulate, meaning to move themselves a limited amount. So for instance, maybe they can move in an L2 ball of a certain radius, or maybe they're a weighted L1 ball, so maybe there are costs to change, changing the X1 feature costs a certain amount per amount you change. Changing the X2 feature costs a different amount, and their goal is to be classified as positive. So think about agents, they get a benefit of +1 for being classified as positive, and they have, cost to move. So they'll only move if it'll classify them as positive, and they'll only move a limited amount because, you wouldn't want to spend more than your benefit in the cost to move. And we'll assume the agents know the current classification rule. So in particular, if the classification rule is deterministic, which it will be in the analysis I'm going to discuss, then agents will only manipulate if it changes their classification from negative to positive, and if they do so, they will do it in the cheapest way possible. Okay. So past work. So there's been other work on this type of problem. Just very briefly. One piece of work by Hart, Megiddo, Papadimitriou, and Wouters looked at a distributional case, and they showed a kind of an interesting thing, which is that if costs are what are called separable, now our model is not separable costs, but let's say you'll tell you what they do. They show that if costs are separable, that actually this strategic behavior can in fact make the decision problem easier. So what does it mean to be separable? So in that model, every point X basically has a height, and the cost to move from one point to another depends just on the difference of their heights. And so one way to think about it is, you might have some complicated landscape and every point has a height, but you can sort of for free move on your current contour line. And you can also move down for free. And if this is true, then kind of no matter how complex the true landscape is, really the only decision a classifier has is sort of how high of a water level to use. What is sort of the minimum height H such that everything above H you classify as positive and below H you classify as negative, because points can move down for free. Really the only thing that matters is the smallest positive point. Okay, so in this model, actually the learning problem becomes easier because there's a limited amount you can do since really all that matters is the height. So it simplifies everything to a one-dimensional learning problem. Our setting, though, is not separable. We're going to have actually cost to move so that you can only move a limited distance. Another piece of related work is of Dong, Roth, Schutzman, Wagoner, and Wu. They consider an online setting, as we do. Their setting has convex losses, and our losses are not convex, but they have a kind of, they allow different costs for different agents, and they have different utility functions. Okay, so what is our setting? So again, our setting is when we have binary classification. We'll have agents that have, they will all have the same movement costs, and they all get a benefit of 1 for being classified as positive and 0 for being classified as negative. And so they will try to manipulate, if they can, to be classified as positive and do it with a cost of at most 1. Okay, so like why is this kind of interesting? So let me just give an example of a challenge. So let's just imagine a case of 2 features like this. And let's imagine that we're in a world where the agents can manipulate their x1 value by up to 0.9. That's how much they can move within their cost budget. But they can't change their x2 value. Let's say the x2 value, whatever it is, is just something that you can't change, but you can change your x1 value at some cost. And so let's imagine linearly separable data like this and running the standard Perceptron algorithm. So one of the classic algorithms for learning a linear separator. So what would that algorithm do? So how does that algorithm work? Well, it starts by picking a positive example and starting with that as your weight vector. And then, so the green vector is the weight vector, the purple line is w.x equals 0, and uses that for classification. So that gets, this positive correctly, this positive correctly. What about this negative? Well, this negative is going to manipulate and move over here. And you're going to then make a mistake because it's negative, but you're going to classify as positive because you're going to see it over here. And then you see it here, what do? Well, the Perceptron algorithm, when it sees a negative example, it subtracts it. So it's going to subtract 0, 1 from 1, 0 to get 1, minus 1. So that'll be the new weight vector, and here's the new decision boundary. Okay, fine. Now what? Well, now notice this positive example here. It cannot manipulate because it costs, this is distance 1 it would have to move, and it can only move up to 0.9. So it can't move far enough to be classified as positive, and so it's not going to move at all, because why pay to manipulate if you're not going to, it's not going to change how you're classified. So it's going to stay put. So you're going to now make a mistake on this positive, and then when you make a mistake on the positive, you're going to add that. So you're going to add 0, 1 to your weight vector. And so adding 0, 1 to your weight vector brings you back to 1, 0 where you were before. And then you'll make a mistake on the negative again, and you'll just keep cycling like this forever. Okay? But notice that there is a perfect linear classifier, that this 1, negative 0.5 would actually have worked. Because if this is your classifier, the positive will manipulate over to here, and so you'll correctly classify it as positive, whereas the negative won't. It can't move that far, and so it'll just stay put, and you'll correctly classify it as negative. So this would be a perfect linear classifier if agents can move, up to 0.9 in the x1 direction. Okay, so this gives an example. You can see sort of where the algorithm, Perceptron algorithm, would just oscillate, but there's still, there is a correct rule. And there's nothing special about the okay, here you could move the x1 but not the x2. Well, this, you can also give an example if, let's say, you can move anywhere you like in an L2 ball of radius 0.5. So let's say, movement has a cost, and the cost to move a distance, d is 2 times d. So at the cost of 1, you can, move anywhere you like up to Euclidean distance 0.5. Okay, so there you can also have a bad example. In fact, the exact same example works as before. Perceptron would start here. This negative example would manipulate and move itself over to here. And so then you'll subtract that to here. And now the positive example, it would like to move down, except it's too far. That's root 2 over 2. And that's too far to move. It can only move up to 0.5. So it'll just stay put. You'll add that like this. But again, this would be a perfect classifier because this positive, let me try to do this without this positive would move, but this negative won't move because it's too far. So the positive will move, be correctly classified as positive, but the negative, if it's more than distance 0.5, it'll stay put. So this would be a perfect classifier. Okay, so a claim is that you can, if we can modify the algorithm though to handle this case, and the algorithm will be different for L1 and L2. I'll give the I'll show the algorithm in the case of L2 manipulation. Okay, so let's assume that the radius r, the amount by which people can manipulate, is known. Don't need that. You can do a binary search in the algorithm for it, but let's for now assume the radius r is known. And let's assume that there exists a perfect classifier if there was no manipulation. So basically the claim is that if there is a perfect classifier without manipulation, we can learn it. Okay, so here is a perfect classifier without manipulation. W star that's greater than or equal to 0. Now, with manipulation, that means there's still a perfect classifier, namely just shifted over by R. So if the purple line is a perfect classifier in the case of no manipulation, if people can, move a distance R, well then just shift it over by R to the blue line, and that will be perfect because, the positives will, this guy will move and the negative won't. And so this will be a perfect classifier. And our goal is to find some W vector that's approximately as W star. Now, so how are we going to do this? So if you're familiar with the way the standard perceptron analysis works, the goal, or even if you're not, the goal is that if we make a mistake, we need to learn something, right? And so if we make a mistake on some example X, we want to be able to update our weight vector by adding some X tilde with the following two properties. One is that this X tilde should have a positive dot product with the true W star, but on the other hand, it should have a 0 or negative dot product with our current vector W. If you're familiar with the standard analysis, right, that first thing increases your dot product with W star, and the second thing makes sure that your length doesn't grow too much, because taking a vector and adding a vector that's perpendicular or strong, or even a smaller angle means that your length is only growing by a little bit, or even could be shrinking. And these two together are enough to get the learning guarantee. I'm not going to go into those details. If you're familiar with it, then you are, and if you're not, just trust me that these are the two properties you want. Okay, so how are we going to do that? We're going to need to have updates that somehow, when we make a mistake, we can update our weight vector using some X tilde that has a positive dot product with the target and a 0 or negative dot product with our current hypothesis vector. Okay, so how is this going to work? Well, we'll start in the usual way. We'll predict negative till we see our first positive example X, and we'll initialize W to that example. Great. And then we'll shift that over by R and predict using the blue line. So we take the perpendicular, shift it up by R, and that's going to be our everything to the right of the blue line will predict positive, and everything to the left we predict negative. Okay. Now, let's look at some easy cases first, and then I'll get to the harder case. Suppose we make a mistake on a positive point, which has a 0 or negative dot product with our weight vector W. So it's on or to the left of the purple line, so some positive like this. Then I claim we can update using it directly. In particular, this point was not manipulated. No one in their right mind would pay to manipulate and still be classified as negative. So that must have been where they started. So that point still has a positive dot product with W star, because by definition, that's what positive examples have, is their positive dot product with W star. And it's a negative dot product with our W because it's to the left of the purple line. So great, we can just manipulate we can update using that. Okay. Now, what about a positive point, making a mistake on a positive point that has a positive dot product with W, so some point here. Now, that would be problematic because, yeah, this has a positive dot product with W star, but it also has a positive dot product with W. So this is going to be a problem. What do we do? Well, we should never see such an example. Why? This shouldn't happen because this point should have moved over to here, because you can manipulate by moving up to R. It didn't manipulate to get to where it is, because you'd never manipulate and still be classified as negative. So this must have been where it started. And if you started there, you would have moved to the blue line. So right. So this will never happen. In fact, if it does happen, this is something you can use if you don't know R. If you're making a guess of what, how far will people move, and you think they'll move this much, right? And you see a point there, then that's a proof that actually your guess was too big. They really can't manipulate as far as you thought. So you can use this in performing your binary search in the case that R is unknown. Okay, but let's assume we know R, and so this will never happen. Great. Okay, so that case is handled. One more easy case. What if we make a mistake on a negative point that's strictly to the right of the blue line? Well, if you're strictly to the right of the blue line, then you didn't manipulate to get there, because you'd never pay extra to manipulate. If you're going to manipulate, you'll just manipulate to the blue line, not past the blue line. So this must have been a true, really a true negative. So this thing has a negative dot product with W star. So just do the usual perceptron thing, which is you just flip it through the origin, and now you get something with a positive dot product with W star, and it's to the left of the purple line, so a negative dot product with our current weight vector. So we just update using that. So that's also an easy case. Okay, so the one last situation that we haven't covered yet is, what about a negative that's actually on the blue line? So this thing manipulated, and we don't know where it manipulated from. So here's what we'll do. We'll pull it back to the purple line, so subtract R times W over length of W, and then flip it through the origin, and we'll use that. Okay, so this at least satisfies this thing because it's on the purple line, so it has a 0 dot product with our weight vector W. But why does it have a positive dot product with W star? Well, the reason is the following. So first of all, our weight vector W always has a positive dot product with the true target. Why? Well, because we initialized to a positive example, which had a positive dot product, and we always added things that had positive dot product. So our dot product W star only increased over time. It started positive and increased over time. Now, where did this point come from? Well, you only manipulate perpendicular to the classifier because you're trying to do it in the cheapest way possible. So it must have come from some point, this yellow point here, somewhere that's straight on the between these two negatives. So by moving it to the purple line, we're only moving it straight back. We're just subtracting from the true point we're subtracting some small multiple of W. And since W had a positive dot product W star, subtracting a multiple of W only made this thing more negative. We subtracted something with a positive dot product W star. So we just made it more negative. So when we flip it, we just made it more positive. So this thing indeed will satisfy this positive dot product with W star, and everything works fine. Okay, so you can extend this to known weighted L1 costs. The game is a little different then, because in the L2 case, you're always manipulating perpendicular to the classifier. In the L1 case, you're always going to manipulate along coordinate axes, but which coordinate axes depends on the classifier, right? So as your classifier kind of like this, maybe you manipulate in the x1 direction. As you tilt it more this way, you'd start manipulating the x2 direction. But if you know what the costs are and you know your current hypothesis, you can compute which direction people will manipulate, maybe not how far, but you know which direction, and then you can use that the same way you used here. Now, if you don't know the costs, it's more complicated. For unknown costs, currently we are exponential in number of unknowns. We don't know a better algorithm than doing a kind of a grid search. Okay, but that's where we are. Okay, so to summarize part 2, so we're examining a classic online learning problem. So online learning of a linear classifier, something that goes way back to the 50s, but in this stylized strategic environment. And the interesting thing that happens here is that the agent's actions change as the classifier changes. And so this can cause standard algorithms like Perceptron to cycle, but you can derive manipulation-aware algorithms that can succeed in the case that the manipulation costs are known, or at least not too many unknowns in this L2 or L1 case. And I think it's interesting to consider, other manipulation models and other classification functions in settings like this. And that's it. All right.
All right, let's thank Avrim for the thought-provoking talk. Any questions? All right, I will start off with one question. So earlier in part 1, you gave this model where essentially, you don't have a distributional assumption, right? On the on the selection bias. So you don't necessarily know, for example, exactly what the distribution, of, a presence of a particular example is, right? Given that particular example. I was wondering if you knew, for example, the distribution, can you do a lot better than what you showed?
In the first part, if you...
The first part. Yeah.
Yeah, so under these bias models, if you knew this was the kind of bias that was happening, so actually let me just go to one of these. So for example, if you think about underrepresentation bias, if you knew that's what was happening, so you knew that the positives of group B weren't showing up at the right rate, another thing you could do is you could just weight them more. You could say, let me just take my training data, and every time I see a positive in group B, it gets weight 2, right? Because it's like representing 2, positives. And so you could do that. And actually, it's interesting because in this model, here, demographic parity doesn't do the right thing, but there's kind of something that's similar to demographic parity you could do, which is instead of forcing your classifier to label the same fraction of A's and B's as positive, instead take your training data, reweight the positives of group B so that your training data matches in a demographic parity sense. It's the same fraction of positives, same fraction of B's are positive as A's are positive by weighted fraction. And now just run plain old DRM, and that would work. So there are other things that you could do in this case. Now that actually doesn't work anymore once you start combining these different, the labeling and the underrepresentation. But it is interesting, right? There are other things that you could do in this case. Yeah, I mean, in some sense, I guess our kind of angle on this is we weren't really thinking of this as kind of, necessarily the only way of solving the problem, but more kind of, here's some additional motivation that you might be interested in using, maybe equality of opportunity from a fairness perspective, and then say, here's another reason you might be interested. Is that if data really was biased, maybe it is, maybe it isn't, but if the data was biased in this way, it would do the right thing. It would allow the Bayes optimal classifiers to go through, and it would kind of help lock them in. And so, whereas in contrast, something like calibration, it's trying to match these things where it really gets affected by the bias. Calibration just gets, the bias messes up what it's doing, even if plain old ERM wouldn't. So it actually amplifies the bias, the calibration. So it's kind of interesting just they have these, in these models, of course, I mean, the different models would act differently.
Interesting, thank you. Any other questions? All right, let me ask another question. So in part 2, have you considered possibly, any partially observable cases where, for example, data points don't necessarily observe the classification boundaries?
Yeah, that's very interesting, right? So I think what's kind of unrealistic about this model is this full information. The data points, they know exactly where they are, and they know exactly where the boundary is, right? A lot of real world scenarios, you don't know, either you don't know, like, if you're applying to college, you don't know exactly where you are in the feature space being used by the, the folks and you don't know exactly what rule they're using, right? And so you would then want to you would manipulate anyway. Yeah, so this is very stylized. Yeah, I think it's very interesting. So I guess, I can just mention, some directions that I think are interesting, right? I think that there has been work in that. So there's been, for example, some work on a kind of a zero-dimensional model that says if either you can either study or not study. And if you don't study, here's the probability distribution of your score on the test. And if you do study, here's the probability distribution on the score on the test. And you can decide whether to study or not study, that kind of a model, right? Yeah, I think it's right. I think it's interesting to think, to imagine that, people don't know exactly where they are, or they don't know exactly the boundary. And I think it's also interesting to consider models where, like there's another Kleinberg-Ragavan model where the action space that people live in is not the same as the feature space you observe. So In fact, that's this picture here on this book. Oh, wrong one. This this book here, What Counts and What Gets Counted, is all about the fact that managers, you're trying to measure this this performance, but you're measuring it using these sort of simplistic measures. And so this is like the Plato's cave. So that's a three-dimensional thing, and you're measuring its shadow on the wall. And even though it's this ballerina, it looks like it's an ostrich, right? So this kind of thing. And so it's looking at that issue. Right. So yeah, and also let me just mention something that I think is also interesting in the other, right, in the bias part. We are looking at everything in the kind of infinite sample limit. We're not worried about the generalization errors. I think if you start looking at smaller samples, then maybe issues that don't really matter here, like say underrepresentation bias. If beta plus and beta minus are the same, in our model it doesn't matter. You just take 10 times more people, you'll get the same data. But if you can't, if you have a limited number of people, then as those numbers go down, your generalization error is getting worse, and so that could really be a problem. And so that can be a real issue. Oh, there's a question here. Is there a connection to this work by posing fairness as a constraint optimization problem? I don't know. I can't answer that. I have to actually look at that paper. But okay.
Okay, any other questions? And also feel free to unmute yourself and ask your question directly.
All right. Oh.
Okay, so we do have one question from Shanaki Murthy. What if some agents don't manipulate? I guess, right, it's talking about the second part of the talk where I guess some agents could choose not to manipulate themselves.
Yeah, so in the setting that we are looking at here, the agents all have the same benefit for being labeled positive and the same costs. So whether they manipulate or not, they might not manipulate. And in fact, they won't if there's no advantage to do so. So sometimes agents will and sometimes they won't. But our assumption is that they all kind of behave in the same way. And actually, that's the reason why this setting here is not, it's not a convex loss. So if you think of this, this purple line, right now it's making if you think of say hinge loss, for example, it's getting a hinge loss from the plus that's on the line, the hinge loss from the minus that's on the line. You start tilting it, the hinge loss will stay identical because those points are gonna move until finally you move a little bit and the negative point jumps away and the hinge loss jumps, right? So yeah, so it's not a convex loss. The paper that this one, the Dong et al. Paper, considers a setting which is easier in some ways and harder in some ways. It's harder in that they allow different agents to have different costs for manipulating. So different, some agents are more easily manipulated, some is harder, but they do set it up where it's a convex losses. And so that part makes it easier. So it's kind of it's a little bit different game. But yeah, I think it'd be interesting to consider, this non-convex case when also, maybe some agents can more easily manipulate than others, maybe, different radii. Yeah.
Any other questions? Okay, so we have a question from Wei Long Wang. The question is there any previous work where the agents don't have full knowledge about the decision rule, but only part of it?
Yes. So the work I know of does talk about this. Let's see, if you don't have full knowledge decision rule. Okay, I guess there's two different ways you could do this. One is that you can actually have the decision rule be probabilistic itself, and then they know it, but just it's probabilistic, and so you might not want to manipulate. So basically, if you're you have a certain cost to move, and the probability of being classified as positive is increasing at a certain rate, and that rate of increase is less than your cost, then you won't manipulate. And so that's one kind of thing. The other is this work, right, where it's not they don't know the rule, okay, but it's that they don't know where they are. So this case where if you, you can choose to study or not study. And if you don't study, well, you'll take the, you're going to take the SATs or whatever, and you're not going to study, and there's some probability distribution over what you're going to get. Or if you do study, there's some other probability distribution of what you're going to get. You can decide to study or not study. So there, I guess, it's not so much not knowing incision rule, but you don't know where you personally are going to be because you're trying to make this decision beforehand. So it's kind of similar. That's what I know. I'm sure there's other work.